So the main topic this week is on relational databases. A billion hours ago, modern Homo sapiens emerged. A billion minutes ago, the Roman Empire was at its height. A billion seconds ago, the Berlin Wall fell. And a billion Google searches ago, I was having my first cup of tea this morning. And so it's just to show that how efficient information technology is these days. Indeed, in Google, we have billions of web pages, and still if you search, you have your results within a couple of milliseconds. So if you think about it, that's quite an achievement of modern technology. So data, and I'm going to show some slides here based on a report. The link is below. So data never sleeps, and in this report they compute how much data is generated every minute. And it's a report. It was last updated in 2020, so it's really about the past year. And so during the COVID-19 pandemic. And here you have a nice visualization where you see a lot of different apps that probably use on a daily basis: Facebook, Reddit, Netflix, Instagram, YouTube, Twitter, Facebook, LinkedIn, Amazon. And you have some numbers. So every minute of the day, on average, people watch. Netflix has 404,000 hours of video that user streams. For Twitter gains 300 new users. Amazon ships 6,600 packages. Facebook users upload more than 100,000 pictures. So that's every minute of the day, 24/7. All year long. So that's quite spectacular. So that's the problem we are trying to solve with data engineering. And you can see that there's a growth. So the main growth of the internet these days is also just the number of new users. And you can see that it has a steady growth. So in 2014, there were 3 billion users using the internet. And now we're at 4.5. And so there's a steady growth in the amount of users, and we can only expect that these numbers will grow and grow in the foreseeable future. So what are some trends? So I highlight them, 3 of the most important trends mentioned in the report. And so it's now estimated that about 1 million is spent per minute online. And Amazon ships about 6,600 packages every minute. So online retail is really important. And I think especially this year with COVID, that even people who were not being used to ordering stuff online, that also has changed. So probably the last year has also had an enormous impact on online retailers. Also, we were working all at home, so we're using tools like Zoom or Blackboard Collaborate. And so they host 208,000 users each minute. So that's also the new normal. And then the third point is if you look at the top 5 companies on Wall Street and the S&P index, they're all tech companies. So that's Apple and Google. And economics expects that companies in that index that the expected lifetime of a company to be in that top index is shrinking. So you used to be in 2016, if you were on Wall Street, on average, you were there for 24 years in that top index, and now it's reduced. They expect it to reduce in 22/7 to 12 years. So That's the tenure, and this metric symbolizes the rapid evolution of the business landscape. So yeah, it's really important. So some general information here, and then the 5 V's of big data. So first you have the volume. It used to be about gigabytes. Now it's terabytes and petabytes, and that's the present. And we can expect that this will only grow to zettabytes and so on. The velocity, so every minute there's a lot of things happening on the internet. So the speed at which new data and user content and videos or purchases is quite high. Then the variety of the data, that's also an important V of the big data. So you can have structured data, such as JSON or CSV files, but also semi-structured data and unstructured data. And so with semi-structured data, for example, we mean HTML code on a web page. So you have some encoding. It has the title as a separate block and paragraphs in separate blocks, but it's semi-structured. You cannot query a web page. It does not contain a list of users or a list of topics. It's basically free text with some structure around it. And then you have unstructured data sources such as files, video, pictures. So these are just pixels, or in the case of video, a sequence of matrices of pixels, and there, they don't have any structures. And finally, also streaming data. And you can, like streaming data these days, you have a lot of sensors in your smartphones, but also in all kinds of smart appliances. And we call that the Internet of Things world. So a lot of these devices continuously send a stream of data to the cloud, and there you can have a lot of applications that process that streaming data. So then veracity, so that means that the levels of data quality are also varying. So for structured data, in the old days, you would have a large relational database, completely structured and clean. But with these different variety of data sources, you can also expect that the level of data quality will vary. And that also requires a lot of work for data engineers to just ensure some kind of quality on the incoming data streams. And finally, there's the V for value. So that's the process of turning data into actionable value, so that you transform these different types of data in a fast way, and that you have can produce some value with your data engineering pipeline. So given this changing landscape, so it forces us to change about how we think, collect, store, manage, analyze, and visualize data. So the traditional data management tools and processing techniques do not scale to internet data. So that's really something that has changed, and it's actually only the last 10-15 years that new tools have arrived, like Hadoop, that enable us to process that amount of data. So yeah. Okay, let's talk a little bit about the history of database. So the first relational data model was introduced in the 70s by Kotz. So Kotz, in that time, Kotz was a little bit of a visionary. I think other researchers at that time thought it was a silly idea and that it was not going to be efficient to have a database in the way he proposed it. But yeah, it turns out that it's that's not the case. Then we saw the mass commercialization of relational databases. So RDBMS stands for Relational Database Management System in the 1980s. So SQL was standardized, the structured query language. The ACID properties, we'll go into that in some detail in a couple of slides, were introduced to ensure that data quality is high, that the data integrity is good. And there was also an ODBC standard, so the Open Database Connectivity Standards, to allow to connect with different databases. And so there are different vendors of relational databases. In the 80s, that was Sybase, Oracle, IBM, and Informix. And they all use the same language, which is SQL, structured query language, and you are able to connect with any of those databases using ODBC. Then, since the 1990s, we have larger and larger databases. So this is, of course, driven by the internet. Then, since 2000, there have been a lot of new open source relational database management systems, such as MySQL, Postgres, MariaDB, and so on. And so open source, with that I mean that the code is available for free and is accessible for anyone to edit. And so often in the past, the big companies like Microsoft or IBM provided solutions, but there you don't have access to the actual programming code. And with open source software, you can really download the code and even change that code if you want. So most people don't change the code, especially not for databases, but other experts in the field, they have these communities and they try to improve open source projects, causing high quality products actually. Also since 2000, there has been some awareness about the limitation of relational database and the start of the NoSQL type of database. And so NoSQL actually doesn't stand for not using SQL as a query language, because actually most NoSQL databases also use SQL as a database, but actually the No stands for not only relational databases. And so what were these evolving requirements? Well, one thing is storing more dynamic data structures. We saw that in week 1 or week 2, I forgot, with the document-oriented model and the graph-oriented model. So storing more of these dynamic structures, and also improve processing an increasing volume of data. So NoSQL is also typically used when the amount of data you have is no longer in the gigabit, but more in the terabyte or petabyte scale. And so since 2010, these NoSQL ecosystems evolved and matured. So we have distributed file-based data storage, such as AWS S3 or a Hadoop file system, which we talked about. Key value column-oriented, document-oriented, and graph-based databases, which will be the main topic for next week. And also databases for streaming data. So the databases that can handle a large amount of updates. For example, you can have a temperature reader at your home, a smart device, and maybe it uploads the temperature every second or every 5 seconds to the cloud. And in that case, you also do not want to use a relational database. So let's go to a relational database management system. So in essence, it's a server-client model. That means you start a database server and it runs on usually a separate computer. It can also run on your local PC if you want, but usually it's central because more than one user use the same database. And that server supports remote access over a certain port. So that means you connect using the IP address or the DNS address of the server, and you connect through a certain port, and then you can start with retrieving or updating data stored and managed by the database server. So a typical step would be, if you use Amazon AWS, you start a database in Amazon AWS, and then you select the vendors. So you can use an open source product like MySQL or Postgres, or you can use Oracle. It doesn't matter that much. Of course, if you're going to use Oracle, that will cost more money. But in the end, all types of vendors will offer similar functionality. Then Amazon, if you start a database in Amazon RDS, it runs as a service, and then you can connect using a client. And so I have here this little terminal command, MySQL in this case, and then I have the flag min-h, which means the host, and here you have MariaDB instance and so on. So this is generated by Amazon. If you click on Start Database in the Amazon console, it will return this dynamically generated DNS name. Then you have the port of the process. So usually it's at least for MySQL, it's 3306. And then you have to give your username. So min-u denotes the username, and then min-p denotes the password. And if you type this commando, it will prompt you, and you have to enter your passwords. And then the client connects using an application protocol, for instance, ODBC, and then you can execute SQL statements. So that's how it works. So SQL, what is it? Structured query language. It's a declarative language, and it can be used to query the database, so retrieve data. You can add new data, remove or update data, and you can also create tables. And so for creating tables, we say that those are data definition instructions, or DDL, and for updating a database and retrieving data, we call that data manipulation instructions. And so it's declarative, which actually means it's intended for non-programmers. So actually, the difference between a normal programming language and a declarative programming language is that with a declarative language, you say what you want, but not which steps needs to be executed. While for SQL, you just say what you want, in essence. It's standardized across different vendors of relational databases, and it has a couple of statements, and the most important ones are select to retrieve data, insert to add a new row, update to update some column in some row, and delete to delete a row. And the output of a select query is also a table. So that means you can write a query, you get a table back, and you can use that table again to continue with querying. So again, the three types of SQL commands. So more the data definition side. So you have, first of all, you have administrative commands, such as create user, create role, and create database. So on one server, there can be different databases, and then you give each database a name, and then you can connect with that database and execute commands on that database. There are also different users and roles. So maybe you have users that have the role, I would say, read only and can only query the database. Or on the other side, you have maybe the administrator role, and he can really delete the entire database if he wants, if he or she wants to. So these are some administrative commands. I will not talk about them further. Then you have the create new table. You can also change a table schema. So that means if you have a table like shipments, and you want to add or remove a column, you can use the alter table statements. Then for data manipulation, you can add rows using insert into. So the syntax is insert into, then the name of your tables, and then the values for each column in your table. You can update a table using update. So for instance, you can update my table, set the value of column 1. Example, the last name, you can change it from some value to another value, and then where specifies the condition. And then thirdly, delete from, you can delete one or more rows from a table. And then the next step is the third type of SQL command is for queries. So queries are used to retrieve information either from one table or multiple tables using join. And the syntax is select and then some columns, the columns you want to select from the table you want. It can be also multiple tables here, and then where specifies the filtering. So if you only want data from this year and you have a date column in your table, you can say where current date time is larger than 2020 and smaller than 2022 or something like that. So the relational model, we talked about it, but I'm just going to repeat it quickly. So basically the data is stored in tables or relations, and we use rows, or also called tuples, and columns. So here you have a nice visualization. So each column contains typically a simple atomic value. So that means a number or a string or an integer or a date. And the values in the column have the same type. So within one column, like age, you expect them all to be integers. So yeah, the types: integer, date time, varchar, decimal. An important value is null. It's like none in Python. So you can also have an empty value, and we use null as a special value for that. And there are also other constraints possible. So you can, for instance, say this column can never be null, and then you say it's not null. But you can also say it's an integer, but it must be bigger than 0, or it's a string, but it can only be in this small set of predefined values, things like that. So we call these restrictions constraints. And then finally, each table has a primary column and 0 or more foreign keys. So a primary key, so here in the example, we have a name table with users on the left, and you see that each user has a unique ID. So for Niels de Preter, the unique ID is 1001, and that column, that ID column, we call it a primary key. So it's used to identify each tuple, and it must be unique for each tuple. And the same for address. There, the primary key is also the ID, or the address ID. That's the table on the right. And so here, Koekoekstraat 1 in Bella, it has a unique ID. So that means there's only one address with that ID. And then a foreign key is really simple. So here, instead of storing all properties of an address within the user table, we just store the ID of the address. And it's a reference or a foreign key, or a link, if you want, to another table. So very, very easy to understand that. Okay. Then some components about a database. So a database, we're not going to talk too much about internals of a database, but there are two components that are important to shortly address. So here is a schematic of what a database actually does inside. So the main thing of a database is you store all the data on disk. You have your secondary storage device, which is a disk. Yeah, it has a tape here, but usually these days it's a solid state disk. And on disk you store all the data. You also store the metadata, so that means like the schema, the definitions of all rows and columns. The database also manages some statistics, for instance, how many times each table is accessed, which are the current users logged into the database, things like that. And it also has a log. The log is used in case the database crashes. So in each database, you can turn off the power at any moment. And then if you restart the database, it has a number of components that will make sure data is not corrupted. And one of these components is the log. So there you save the current ongoing transactions. And if the database is then shut down, it's saved in the log. And then a lot of components here, but we'll talk about transaction manager and the query optimizer. So what is a transaction? Here's an example. Here I have 3 queries. Select balance from account, update account, and again update account. So 3 queries and some code. And you see the first and the last line is start and end transaction. And what this piece of code does is actually a bank transfer. So I have my from account, maybe my regular account, then my to account, maybe my savings account, and I want to transfer 200 euros. So the first thing I do is I retrieve the current saldo from my regular account. So I select the column balance from the table account where the account ID equals that variable, so BE 2020 and so on. So, and then I have my current balance. And if that balance is higher than the amount I want to transfer, so if I don't have 200 euros on my regular account, I cannot transfer that amount to my savings account. So there's this check. But if that's true, then I update my current account, and I set the balance to be the balance min the amount you want to transfer from my from account. And then I update my savings account and I set the balance to balance plus amount where the account ID equals the to account variable. And so ending with 555. And so this is one example of a real world query. And of course, it's interesting because you want this to be executed as a whole. So you can imagine what happens if I update my balance, my regular account, and I update it and set it from minus 200 euros, and then the database crashes. What happens then? Yeah, that's a real problem. So you want these transactions to be atomic. That means either it executes as a whole, or if it like crashes after the first update statements, the server, then you wanted the results rollbacked. So that's what in essence a transaction is. So you can imagine that's very important when you do bank transfers, but also for a number of other applications. That's an important property. So yeah, what can go wrong if the database server reboots after executing the first update statements? Yeah, in the end, I transfer maybe 100 euro. It gets subtracted from my balance. Then the server crashes and I lost my 100 euros. It's virtually gone. So that's something you want to avoid. Another thing you want to avoid is if you have at exactly the same time two users running the same transaction. So for instance, I can call my wife and let's say we have 100 euros on our regular account, and me and my wife at the exact millisecond, we both want to transfer 100 euros. So normally that's not possible because you have the if statements that checks the saldo. So if there's only 100 euros, you want to transfer 100 euros, you can only do that once. But if we do it at exactly the same time, after the first select here, at the same millisecond, at that time, my database will contain 100 euros. So if two users do it concurrently, you might end up with a negative balance. So that's something we have to take care of. So if two transactions run concurrently, we have to do something about that. So that's where the transaction manager comes in. So with the transaction manager, you have a transaction and either it commits, meaning all the results are saved to disk in a consistent state, or it's aborted. So either my transfer, if I execute my my transaction with my transfer in the database, either the relational database say commit, which means everything is saved, and even if the database is the power is put down, it's saved your data, or the transaction is aborted, meaning all partial changes are ignored. So if the database crashes after the first statement and subtracts from my regular account but does not save to my saving account, then you want to ignore that change. And so that's called rolling back the transaction. And we have these ACID properties. So ACID stands for atomic, consistent, isolated, and durable. So atomic means either the transaction performs as a whole or it's completely rolled back. So no partial changes are stored. So that's the first property. Second property is consistent. So that means after the transaction, the database is in a consistent state, or the transaction is rolled back. So consistent, that means, for example, if you have a foreign key to another table, and then you delete some row, that should not be allowed. If you reference another column in another table using foreign key, that should be present in the database. So that's one example of being consistent. And then isolated, that means that transactions are executed in isolation, meaning if you have the same transaction or different transactions but executing on the same data by different users in parallel, that they do not interfere with each other. So for instance, here the case with where you have two concurrent updates. So what we want is that each of those concurrent updates is isolated. So you do not get the temporary partial results from somebody else who's updating the same data at the same time. And the last one is durable. That means if a transaction completes or commits, it cannot be undone. So that means if your transaction is finished, your data is saved in disk and it's safe there. So that's what you want. And so there are different algorithms to get these nice properties. And these algorithms, they are all have been invented to ensure isolation and control of concurrently running transactions. And the most common algorithm for concurrency control is two-phase locking. So two-phase locking means that in essence that you take locks. So if I update the balance in my table and some other user wants to read or write to that balance, he cannot. He has to wait because the data is locked temporarily by me, by my transaction. So that's one way to deal with multiple users accessing the same data. It's with locking. And there are two types of locks, a read lock and a write lock. And a read lock is actually that you say to the database, okay, I'm reading my current balance, and other transactions happening at the same time, they can also read that data, but they cannot write to that data. So for instance, if I'm reading my balance, then that means that not at the same time another transaction can update that balance, because I have a read lock. And if another transaction wants to update that balance, they have to wait until my transaction is finished. So that's one type of restriction. Another type of restriction on concurrent access is a write lock. And a write lock is a little bit more strict. So if I have a write lock, that means I want to update my balance. I request a write lock on that. And if I have this write lock, that means no other transaction can read or write that row. Yeah? And then at the end of the transaction, you release all read and write locks, and then another transaction can use the same data or whatever. Yeah? So here's an example with a bank transfer. So here you have two users, and the first user selects the balance from the account, and then he requests before that select statements. Behind the screens, what happens is the database, or the transaction manager, which uses the two-phase locking algorithm, requests a lock reads on that balance row. Yeah. Then at step 4, you have another transaction started, and it also wants to read the balance, but that's fine. So two transactions can read the same value as long as they don't write to that value. That second user can continue with that statement. Then we have time step 7, and there the first transaction requests a lock for writing to balance, because I want to update my account and withdraw 200 euros. So I request a lock on a write lock on that balance, and then the other transaction also wants to write and also wants to update that account, but he has to wait. So because of the lock that has been requested, he has to wait. Or also that's a second option. It can also be that the transaction is rolled back, so that the second user gets a message saying that you cannot change the data because it's in use or something like that. Then at step 9, we execute our first update statement. Then again, we want to update our savings account, so we request a second write lock on balance 2. And then finally, we release all locks and commit the transaction. And at that time step 14, actually the second transaction continues. So it was halted before because of the locks, but now the locks are released. So the second transaction can also continue with withdrawing to 100 euros and transferring to the other account. And so that's basically the locking mechanism. So two-phase locking guarantees that all transactions are executed serializable. So that means if you have two concurrent transactions and they're planned using two-phase locking, that T1 and T2 are executed in an isolated way. So the effect of executing T1 and T2 is the same as serially executing T1. So that means first executing T1 and then T2. So that's what two-phase locking guarantees. There's a possibility of deadlock. So deadlock can happen. So what's deadlock? For example, you have a first transaction, but that's waiting for some locks to release on a second transaction, T2. But then T2 is also waiting on a third transaction, T3, and then T3 again is waiting on T1. So here you have a cycle. And obviously, it's deadlock. So if T1 is waiting on T2 and T2 is waiting on T3 and T3 is waiting on T1, this will never get resolved. So these three transactions are dead. So one trivial solution is then to roll back one of those transactions after some seconds. So that's a timeout. So that's one trivial solution to get out of deadlock. And then a third point that's important to mention is within NoSQL databases, they typically do a different trade-off. So with transactional data, that's quite good if you're doing online analytic processing and in applications such as making reservations or financial applications. You really want those transactions that are isolated and durable and so on. But in different scenarios, like maybe a chat online or a social network, it's not that important that you have this ACID properties of a transaction, and there's more focus on higher throughput. So that's within NoSQL. Okay, I'm going to continue now with the query optimizer and indexes. And after this couple of slides, I'm going to take a small break. So what is the query optimizer? Again, an important component of the relational database. So we saw before, SQL is a declarative programming language, meaning you specify what you want now, not how it is implemented. So it's actually the query optimizer that attempts to determine the most efficient way to execute a query. And also it uses indexes. So the relational databases uses a number of indexes, and the query optimizer uses that to make the queries more efficient. So what is an index? An index supports fast searching for a column or a set of columns. And internally, it uses either a variant of a binary tree, which is called a B+ tree, or a hash table data structure. So the data structures we saw last week, they're also used internally for databases. By default, you can expect that the primary key and also foreign keys are indexed. And so these indexes or data structures, they're implemented as a kind of special purpose table, but they're only accessible by the database management system. So as an end user, you cannot directly access those indexes. They're just used internally to speed up queries. One important thing is that indexes typically speed up selects. So you can typically speed up searches, and queries are going to get faster. But if you have an additional index, it also slows down your inserts, updates, and deletes. So the reason is, if you delete data that's indexed, you don't only have to remove the row from storage, but you also have to update the index. So you have two things you have to update, and the same is for adding new data or updating data. You always have to change the row data structure, but also the index data structures. So that's why indexes can slow a little bit down those operations. And then the final point here is that creating the optimal set of indexes is an art, because you have to balance the speed for executing certain types of queries versus the speed of adding new data. So that's an index. For instance, here I have a user table with ID, name, and city, and ID is my primary key, which means by default it is indexed. And if I then type a query in SQL, so here I type select name, city from users where ID is 11. So what does it mean? It means I want the columns name and city selected from the users table where ID is 11. So here that's Adams, Athens, user name Adams in the city of Athens that I want to retrieve. So if I'm going to execute that query, internally the query optimizer is going to use the index. So we have an index on the ID column, and it's a B+ tree. So that means it's like a binary tree, and in the left branch and in the right branch, in each subtree, you find all rows with an ID that are higher or lower. That's how it works. And at the bottom, at the leaf, at the bottom of the tree, in the leaves, then you find the actual values of the different columns in each row. So that's how it works. So that means it has an average complexity of of log n to search data. So even if you have millions of data points, log n is going to be a small number. And on average, you're going to do this log n type operations to retrieve your data. So that's what an index is. And one difference between a B+ tree and a binary tree is that a B+ tree doesn't necessarily split each branch in two. So here, like for example, the right subtree, you have 23, 31, and 43. So that's a three-array node. That means all values smaller than 23 are stored in the left branch. All values between 23 and 31 are stored in the center branch. And all values higher than 43 are stored in the right branch. And then between 31 and 43 in the third branch. And so that's a difference. So the query optimizer attempts to determine the most efficient way to execute a query, and it does that by considering different possible query plans. So the planning takes the table size and available index into account, and I have an example here. Assume you want to execute this query. So this is a query over two tables. So I have from user and address. So I'm going to query both tables. I'm going to select the user first name and last name. And from address table, I'm going to select streets and the city column. And then the condition where. And then we have a join here. So we say the address ID of the user must match the ID in the address table. So those have to be equal. So here in the first row, you have Niels Preter. He has an address ID of 114, and that matches the address table where you have an address with ID 114, which is in the Lange Lausanne-straat 202 in Antwerp. So that's what we want to return. So we're going to find for each user a row in the address table with the same ID, and also the condition that the first name of the user equals Niels. So Niels must be equal, and address ID in user and ID in address must be equal. So that's the query. So join. So we have two plans, and the query optimizer, before it executes anything, is going to enumerate some plans. So the first plan is we can merge or join all users and addresses. So that means we're going to loop over each row in users, each row in address, and we're going to return rows where the address ID equals the ID in the address table. So that's a merge. That's plan step 1. And then step 2 is, given those merge results, we can just filter on the users with first name Niels. So the first step, you can make use of indexes. So both ID and address ID are keys. Address ID a foreign key, ID a primary key, and they're indexed. So that's efficient to then merge that data. The second step is not that efficient because we have no index on first name. First name is just a column. So unless we have specified it, it typically will have no index. So that means a full row scan. So that's option A. Option B is that we first, in the user table, filter all users where the first name is Niels. So we're gonna maybe return one or a couple of rows where users have the first name Niels. And then in the second part, we're going to merge that small table of users with first name Niels and find matching addresses. So that's the second option. So both plan A and B compute the same answer, but you can imagine that plan B is more efficient because there will only be a small number of users called Niels, and we only have to match for those small set of users the address. So plan B is probably more efficient, and the query optimizer can also does this type of reasoning and continues with plan B then. So that's what the query optimizer does. It can be that sometime your query is still too slow. So there are two options then, what you can do. The first is you can add indexes yourself. So you have the syntax, create index name on table. And for instance, in our query, we could have created an additional index, not only on the user ID, but also on the user first name, or on the combination of user first name and address ID. So that's something you can do. The second thing you can do is type, and not all environments support it, but like Postgres definitely supports it, and it's explain. That's a special command, and then you write your select query, and then you get a plan. Then you get a plan what's going under behind the scenes, and the query optimizer returns its plan. So there's an example here, and you can see that this is just an example I took from the internet, but you can see that in this plan they use a quick sort and a hash join, and then a sequential scan, and then again a hash data structure. So quick sort, hash tables, binary trees, those are all types of indexes and algorithms used to solve a select query. And the query optimizer tries to make the most efficient plan. Okay, so that concludes the query optimizer. Before we continue, I would propose we take a small break and then finish the rest of the slides. Good, so 5-minute break and then we'll continue. Hey, let's continue with the presentation. Okay, where was I? Transaction manager, indexes, query optimizer. Okay, so the second part of this presentation is more hands-on. So we'll start with an example schema. So this is an example that can maybe used in some warehousing application. So we have a couple of tables, and the first table is the supplier. And so what is a supplier? Well, he has a unique SNUM. So that's a primary key, a unique value that's unique for each row. Then we have the name, the status, and the city of the supplier. So the first supplier is Smith, a status 20. Not sure what that means. And that supplier is located in London. Then we have the second table, which contains parts. So you have maybe some bolts and screws, and each part has also a unique code. So PNUM, that's also the primary key, and each part has a certain color, a certain weight, and also a city. So that could be the city where it's produced or something. And then we have a third table, projects. Here we have a unique code in the enum column, which is also the primary key. And each project has a name and also a city. And so this can be some kind of device, like a tape. That's maybe project A7. And then it's associated with parts and also the supplier for each part. So that information is stored in shipment. So here we have 3 columns, SNUM, PNUM, and YENUM. And these are foreign keys. So that means SNUM, S1, refers to an entry in the suppliers table. So it's a foreign key to the SNUM column in the suppliers table. PNUM, with here the first code P1, is a foreign key to the parts table, to the primary key there, the unique part number. And then YENUM, because part and project both start with P, they decided to call it YENUM, is a reference to the project. And together, this combination of 3 columns is unique. So for each row, we can say, for instance, S1, which is, let's go back, Smith, who's the supplier from London, has supplied or has shipped, part P1. So P1, that was a nut, a red nut, weighing 12, I don't know, grams or something. And that's the supplier of that part, of that nut. And then the project, YENUM, it's for a sorter. So maybe that's a kind of sorter machine used by some companies that contains that red nuts. And there are 200 of these ordered and shipped at that specific time. So that's the shipment table. So that's a nice example of a traditional database. Here we show the entity relationship diagram. So that's a visual diagram which summarizes the different tables. So here we just have the different tables, so suppliers, where we have all the column names and also the types. So varchar 5 means it's a variable length string with at most 5 characters. And status is an integer and so on. And the legend also shows the primary key, so the unique code in each table, and also foreign keys which are underlined, so shipment, references, supplier, project, and parts. So that's a typical schema. And then given that schema, I show some examples of how to add, remove, or update data. And so to add data, you can just use insert into. So the syntax is insert into table, and then the columns of that table, and then the values you want to insert. So for example, if you want to add a supplier, you can write insert into supplier, then all columns of the supplier and the values. And this will add supplier S99 with a supplier name of Watson, 25 status, and city is Oslo. So that's the first example. Then you can update data. So the syntax is update table, set column 1 equals to value 1, column 2 equals to value 2, and so on, where some condition. So where some condition. So in this example, we update the suppliers table, and we set the status to 100. So we change the value, in this case, for all suppliers in the city of Athens. We change the status from 30 to 100. So using update, you can update a single row. For example, if you here write where snum equals s5, you can only update the row of Adams, or we can have another condition and then you can update multiple rows using one command as shown here. Can you add multiple conditions? Yes, you can add multiple conditions. So here in the where clause, you can write and, or, and you can say where cities Athens and S name is Adams or something. So you can use all kinds of logical conditions in the where clause. Then you can delete rows from a table. So deleting is just delete from table. And then again, you specify a condition. So here also you can have multiple conditions. And here's an example. So to delete all rows in the suppliers table, you write delete from supplier where city is Paris. So in this case, the row with S name Jones and Blake in which are in Paris get removed. So very simple. One thing you have to be careful about is referential integrity. For example, if you delete from supplier where snum is S1, the database will probably fail and show something like the delete statement conflicted with the reference constraint. And what that means is that the supplier is probably referenced from the shipment table. So that means it's referenced. It also means there's a referential integrity constraint. So shipment refers to a certain supplier, and if you then delete that supplier, then your data is not clean anymore because you have a broken link. So that's not allowed. So how do you circumvent this problem? Well, first you delete rows from shipment 10. So shipment refers to supplier S1. So first you're going to remove all rows with a reference to the supplier, and then you can safely delete the supplier and the database will say it's fine. So that's one thing you should be aware of. Then the next thing is querying data. So retrieving data from a table, and the format, the syntax is select from where. So you select the columns you want to return. Sometimes you don't want to return all columns, but just a couple of columns. So you have to specify them here. If you want all columns, you can type star. So asterisk, symbol asterisk, and then it returns all columns. From table, so it can be a single table or multiple tables. So here it's one table, and then where you specify the conditions. So here we have a condition that the column 3 must be equal to value 1 and column 1 must be equal to value 2. So here's an example from again with the suppliers table. So here you want to return the column snum, sname, and status. Where there's a little error here. It says quantity in the column, that should be city. And so where city is London. And so in this case, it will return S1 Smith 20 and S4 Clark 20. And so note that the result is also a table. So what you often do in real world SQL queries is combine different subqueries into one bigger query. So that's a simple select. Then you can retrieve data from multiple tables. To do that, you write a join. So this is an example of an inner join. So here we select a column from table 1 and a column from table 2. And then we say from table 1, inner join table 2 on table column 3 equals table column 4. So here you will join. So you will select all rows from both tables that have this condition. And like in the example before, it was with user and the address ID. That was an example of an inner join. So here's another example. Suppose we want the supplier name, the supplier city, and then the shipment quantity and the time of the shipment. Then we select these 4 columns. In the from class, we write supplier inner join shipment on supplier snum equals shipment snum. So then we only have shipments that match with the corresponding row in the suppliers table. And then here we have an additional condition, but that's optional actually, where shipment snum equals S1. So this will return all suppliers with the code S1. The quantity and the timestamp are from the shipment table, and the S name and city are from the suppliers table. And we call this an inner join. So there are, here's another visualization. So here we have our tables. So the requirements, in our query, we had where shipment snum is equal to S1, but also supplier snum must be equal to shipment snum. So that means both in the supplier and shipment table, we're only interested in a row which are about supplier S1. So these are highlighted in yellow. And if we merge that information, we get just 2 rows where we duplicate the name of the supplier and the city 2 times, and then we have 2 times the quantity and the shipment date. So that's a way to get to combine data from different tables. And there are different types of joins. So the inner join is really like the set intersection between 2 tables. Only the difference with set intersections in maths is that we don't have only we do the intersections on keys, but we also want the other columns. So the intersection is actually on all values where snum matches the snum column in the shipment table, but we also want the other columns. So it's a little bit different from a mathematical set intersection, but the concept is similar. So that's an inner join. You can also have a left join. For example, suppose we want all shipments and join that, do a left join with the suppliers table on snum. But suppose some shipment doesn't have an snum, then the snum is empty in the shipment table. Well, if you do an inner join, you do the intersection, so you lose that row. But if you do a left join, you still get all shipment rows, even if snum is null or something like that. So that's one option. Right join is the other way around, so that's similar. And then we can also do a full outer join, so that means you don't lose rows in the join if they don't share a value as specified with the on criterion. So these are the types of joins. And then the final variation on select is the group by clause, and group by is used to compute some statistics on groups. For instance, you can select a column and then count stars from table 1, and you group by that column 1. So what does it mean? That actually it means that all rows that match the same value of column 1 will be in one subgroup, and within that subgroup you count the other columns. I'll show an example in the next slides. And then you can have a condition on count star, so that's the number of other tuples with the same value of column 1, and you can have a condition of that using the having clause. So that's like a where. The only difference between where is it works on group aggregate functions. And aggregate functions are the usual functions from statistics. So you have count, the sum of values, the maximum or the minimum of values. And you can have conditions on that if you want in the having clause, but it's optional. So here's an example. If you want the number of suppliers in each city, what you do is you group by a city, and that's shown here. So the first group consists of the 2 suppliers from London, then the second group is 2 suppliers from Paris, and then the last group is only 1 row with the supplier from Athens. So that's what group by does. And then you return count star, so that means the number of times a row in each group occurs. So for London that's 2, for Paris that's also 2, and for Athens that's 1. And then you have the condition on the count, so you say having count is 1, so that means that for Athens we only have 1 supplier from Athens. So the count is 1 and it's filtered from our results. And so that's a very simple example of group by. The group by is very powerful, and you can imagine that grouping and computing statistics on some columns, that's very useful to do when analyzing data. Okay, then a final note on queries. So I showed you actually all you need to know about SQL. So with these selects, joins, group by, where, and from, you can do pretty much any possible query you can imagine, but in the real world it can get complex. So these are all simple queries about 3 lines, but in the real world often a query of 100 lines is possible. And I've shown an example here of something I was working on last week for Frumel, the company where I also am employed at. And here it's just an example. I'm not going to get into details, but basically I compute the number of recommended items per age. So recommendations are suggestions shown, for instance, on the Dreamland websites, where you get suggestions like, okay, I clicked on a Lego product and I get other interesting Lego products. And with this query, I compute how old these products are. So that's a more advanced query. And you see here, first I use the width class. So that means I create like a temporary table called recommendations. And then I do a select of different columns, but I also use some functions like timestamp seconds, which is a transformation of a column stored as an integer to a date-time format. Timestamp diff, which computes the age in hours. So if an item is 1 hour or 2 hours or 3 hours old, relative to when it was recommended, I compute that difference as age hours. I also use the function JSON value. So it's also possible in a relational database to store JSON as a column type. And so not only a string or a datetime, but really a little document in JSON. And here I extract 2 properties of that metadata stored in JSON. And then I do an inner join. And then I here have a condition where I say, oh, I'm interested in all data between 12 and 16 February. Then I have some conditions on other attributes. And finally, I sort the data by date and then by the ID of the users and then the rank of the recommendation. So given this view, I then do two group bys, and in the first subclass, I use my table defined here above, and then I count the number of times an item was recommended, and I divide it by the total amount of total times it was recommended. And by doing this, I get the average age of recommendations and the total amount of recommendations for each age of products. So that's just an example to give of a real-world example of a more advanced query. So some use cases for relational databases. The classical use case is known as an operational or transactional database, and then we do something called online transactional processing, or OLTP. And so that's what you expect, for example, if you're doing bank transfer in financial applications. That's typically online transactional processing, because you have a lot of users and they all want to do transactions such as bank transfers or things like that. Same goes if you have an online shop, an online retailer, and a transaction is then a purchase of one or more products. That's also a typical online transactional processing type of application. Lots of things like that. So it's pretty major use case. And what you do is you store current and also historical data, and typically the data is organized in a normalized data structure. So normalized means you have as little redundant data as possible, and you do that by storing everything into separate tables and then linking the tables to each other using foreign keys. So that's called normalizing. And an advantage of that use case is with a relational database, you can support a high volume of transactions each second. So that's one use case. Some other examples here: airline booking systems, KLM, Air France, e-commerce ordering, Amazon, also online content delivery, so like Netflix and YouTube. So there are two components. So the actual streaming video, it's not stored in a database. That's a file stored maybe in something like AWS S3 or something like that. But all the metadata, like for each movie, you have the actors, the title, a link to a small banner of the movie, things like that when it was released, and that can be perfectly stored in a relational database. Also, which users have comments on the video, like in YouTube. That's something that could also be stored in a production database. Some limitations to relational databases. So if your data does not map neatly into rows and columns, then the relational model is maybe not the best choice for those types of data. And also is that advantages can become drawbacks. So we talked about asset transactions. So transactions are really nice for bank transfers and purchases and transactions and applications where the concept of transactions is important, but it also slows down a little bit. So if you go back to the first slides with the 400,000 users looking at connected to Zoom at 1 minute, that kind of data volume, transactional processing will cause some delay, so that might not be feasible. Also in database, you have a static data structures, which means everything is defined, and of course you can add a column, but if you're going to add columns or new tables every minute or every hour, then that no longer gets manageable. So that's also both an advantage and a disadvantage. And finally, while relational databases offer fast and efficient access to individual records, it can be that also is maybe good for some applications, but a problem for other applications. And so, like if all data is in individual records, that also means you have to join a large number of tables to do analysis. So if you're only interested in doing analysis on your data, you can there are better solutions to use, and we'll see that next week. Okay. I think that concludes my presentation. I have some additional information here about schema and normalizations, but I'm going to skip that for now. So yeah, that concludes this presentation. In the afternoon, you will do some exercises together with Janou Ramon on SQL, and we will use an online tool for that. So since we have a little bit more time, I'll quickly show you the tool. Wait, I'm going to share my screen. So this tool, is it visible to everyone? Yes, okay, fine. So SQL Fiddle can be used, is a simple tool to just run some queries online. So you just go to this website, and then I'm going to use a schema I made last year. So for a social network type of applications. So I'm going to copy paste my code here. And basically it has the create table statements and some insert statements. So I'm just going to run this and type build schema. And then I can here see what I have created. So I have 8 tables like users, which has a email, first name, last name, also message, like the messages from each users and so on. So that's my schema. And then I can run some queries here on the right side. So for instance, I'll zoom in a little bit. Select all columns from the table user. So that's my first query. I type on execute, and then here you have some tuples. So you have Len Veremans, first name, last name, birth dates, Peter Sely, Toon Kalders, and so on. So that's one simple query. Then I can have a condition like where last name equals Veremans. So that's an example of just using the where class, and then I get back one row. Then I can combine several tables. So for instance, let me look at the message table, select star, or maybe the my group table. Select star from my group. So there's one group called database fans, and then maybe select the member table. What's this type of table? It has members, and then you have the group name. So if I now want a list of users together with their group name, I can join the member table with the user table. So I can say select from user my members. Member where, and then you see here you have a user email, which was also a property in the user table, but there it was called email. So then I type from user inner join members on user email equals members. user email. So if I run this, I get all the columns of both the users and the member table. So I now have the email, first, last name, and also the group name. This field is duplicated. So maybe we're only interested in first name, last name, and group name. And I can just specify that in the selects. So I can also insert data. So let's say in my group, I only had one group. If I remember correctly, my example database. So I can add another group with insert. So insert into my group values and then the name of the group. Let's say data engineering fans, and the administrator is lenveremans@uantwerp.be. So if I execute this, only in the query panel. Okay, I think I have to add insert. It's just a tool here. I have to write it on the left side. So, okay, I think it's okay now. Select there from my group. Run that again. And then you can see we have two groups now. And then we can do a group by. For instance, count the number of members in each table. So I can say select star from members. So, sorry, exit full screen editor. So I have my member table here with all the members and their groups, and then I can, for instance, count the number of members in each group. So I type count star. I select the group name. I group by group name. And I count the number of members for each group. So here I have three database fans. Yeah, I had my data engineering fans table, but there wasn't any data in it. So to add some data here, maybe interesting. Insert. I can insert a new member. It's not that's important. I'm gonna quit this. Refresh. Okay, voilà. Browser, yeah. So yeah, using this, you can quickly execute queries, and it will be used during the lab session to practice a bit the SQL query language. Okay. Okay, so this concludes this lecture. Any more questions? Any questions, anyone? Is it all clear? Okay, okay, all clear. Thanks for the lesson, Manuel. Yes, no problem. You're welcome. Okay, so see you next week. Bye.